Все, раз, два. А какой еще должно быть? Раз, раз. Эхо. Наверное, за этот колонки. Курсия пошла. Зеленую можно закрыть. Все? Начинаем? Okay, let's start. Today I'd like to talk about how machine learning can conditions. First let me introduce myself a little bit. I'm a graduate of Moscow State University in Beloglazov. I graduated about 10 years ago. I studied maths and computer science. Currently, I work mainly as project manager of the freelance team, and I have some very basic machine learning knowledge. But that's not the whole background that I have. I also orchestrate, compose music, record, perform, sing, play various instruments, as you can see. And I also write songs. So before we move on to the next slide, tell me what kind of audio formats you think is most popular. So when you think of music on the computer, what kind of files do you think of? Yeah. So that's the most popular format. Let's jump to the next slide. So first of all, I'd like to give a very, very brief introduction to two types of digital music, so to say. So there is audio and MIDI. Audio is, so first of all, what is the sound in the music? It's basically the air pressure variations. So the air vibrates and we perceive it with our ears, and we hear it somehow. Our brain interprets this, and in the end, this is just the air pressure variations. And so if you before the computers era, there were recorders like tape recorders or something like that, and they basically converted the air pressure variations to some other variations, so voltage variations, and something else. So what audio stands for in computers, digital audio, basically it's the converted variations of the air pressure into a digital representation, and it's sort of an approximation. It's usually it's compressed like MP3. It's compressed format. The most common format used for recording is WAV, WAV, and it's closer to the original signal. It's not so compressed or something. But there is one other format which is very important, but it's not well known by common users, so to say. It's MIDI, and you might have heard about it. It's also quite popular, and especially it was popular 10 years ago on old phones. You could download a ringtone MIDI format. So what is MIDI? MIDI stands for Musical Instrument Digital Interface, and it's sort of a musical score for computer. It's like, so when a musician plays music by paper, he sees the notes, he sees the instructions, and so MIDI is the digital format for these instructions. It contains the instrument information, note start and duration information, no pitch, no velocity, like how hard the key should be pressed, etc. So actually, there is a picture here. It's not a very good representation of audio and MIDI. The next slide represents it better. So this is how audio and MIDI look inside a couple of popular music editors. So on the left, you see audio. It's the waveform. Basically, it represents the amplitude of the signal. So it's on this axis, and this is time. So we have some maybe a phrase or something like that. So it starts from silence, then it goes up, it becomes louder, then it goes down, then the peak is here, and then it ends with silence again. And this one is spectrogram, which presents the frequency. So here we have low frequencies at the start, and then it goes higher. So maybe it's a kind of phrase. The MIDI looks completely different. By the way, if you look at some song, you'll see it doesn't look like this. It's more. It's like it goes like one piece. It's not divided like this. So it's more like this. And here's the MIDI. It's a piece of music that I worked on. It's the piano part, and as you can see, we see the piano roll here, the keyboard, and it's just for reference for the musician who works on this. And we see the notes. So we see where the note starts and how long it sounds. So these are the notes. And we see at the bottom special information is velocity, how hard the virtual instrument should press the key, or I don't know, hit the strings or whatever. Here's how it looks, and it's just another view of what you see in music score in sheet music, and I'll show it to you later. So in my examples, and let me quickly get back and explain why I started this presentation at all. So my goal is to maybe raise the interest to problems that modern musicians have, and how I see the neural networks and artificial intelligence can be helpful to resolve this problem. So in my problems, I usually work with MIDI to compose music, and audio is for recording live sound like vocals, guitars, etc. And so I suggest to use MIDI to solve the problems that I have, and and you'll see a little bit more why. But first, I'd like to cover very basic reasons why I think we should choose MIDI. First of all, MIDI is significantly less data. MIDI is an instruction, and it's a little bit silly to compare MIDI files to, for example, MP3 files, because they have very different meaning. But MIDI is still, it's like comparing a program and an output of the program. That's, so the MIDI is just an instruction. And also, MIDI is more neutral. Composers think in terms of music score, not waveforms. So here's the picture of Bach, and that's MIDI too. That's the old representation, so to say. So let's quickly jump into what a piece of music is. So I'm going to open this link. So there are basically, so to say, three types of music you can encounter. So the first, the simple one, when you sing in your shower, you sing a melody, something that you sing with your voice. You can sing only one note at a time, and it's also called monophony. So let me play this melody for you. Okay, so that's the well-known Russian song, song, and it's just a melody. It's just one voice. if it if it was possible to somehow yeah, it's a very good question. I think so far what I saw in other projects in this field, I thought they were made just for fun because I didn't see applications. But I know that in the past, they maybe in present too, there was a composer who really used not artificial intelligence, but some algorithms, some machine machine generated things to compose his music. So and it was okay for him. So it's uh, I don't think it's cheap. You don't have to use the material created by a computer and sign it with your name. Like it's I created this, so you can be open and say, okay, I'm using some interesting mechanisms to improve my work or to to have an inspiration. Also, that's I recall that when I started thinking about all of this stuff, I talked to a professional musician regarding this, and she said, "Hey, Dmitry, that's strange. How about art? Music is art. It's not something that's created by machines." And I said, "Look, artificial. The words artificial and art they have the same root. It's the very close thing, and uh, I mean when you create something, when you compose something, it doesn't just go like from heaven. You just sit and record what you hear in your head. No, it's a complex task. You have to follow certain rules. You have to rework. You have to see how it has certain mathematical basis under it. So it's complex work and it could be simplified. So that's I'm looking at this as a means for simplifying some things and looking for some inspiration. So, okay.
Did you try to use debugs for different neural network systems?
Not yet. I was planning to, and in process of I the last thing I learned was TensorFlow. Not learned, but so reviewed it. But oh, and it's a good question too because I forgot to mention my potential role in this kind of project. So, of course, I'd love to just sit and program it by myself, but it would be nice if someone else helps me. And I would be, I have a very solid background in digital music. I know how to program, how to work with MIDI collaborator on this. It's someone who's interested in neural networks and artificial intelligence who's ready to program it, and we could work together. So that's actually that actually was my goal of going here and sharing these ideas.
So, have any idea how to help Dmitry?
Yeah. So if someone is interested, just reach me by email, and be happy to do something great.
Okay.
Okay. Thank you.
So, other questions? Maybe some additional ideas what we can suggest to also to use in music production, music composing.
I think we have this comment. The issue you mentioned about analyzing how music is good, so I think it's some kind of sharing method. Can't get that way. So just in that, that's
Oh, I think that generate adversarial networks is a good architecture for this task, especially because it's useful for producing such kind of something new melodies which are based on those who is known, well known. AI adds some creative creations, variations. Okay, thank you, Dmitry. Thank you. So, and we are going to our next reporter. Okay, Boris.
Mhm. Ну, конечно, да. Ага.
О. Раз. Раз. Два, три.
Ну, все время блок.
Да, вот так вот микрофон работает. Так, а здесь нам нужно выключить звук. Как его выключить? Полностью.
Да. Ага.
Раз, два, три.
Ну, хоть чуть-чуть будет.
Все?
Okay, so today we're going to continue discussing the fourth chapter of Frontiers in Massive Data Analysis article. So it's about some challenges in massive data analysis, and so we consider real-time data processing. So on the last seminar we discussed data acquisition and data storing. Yeah, it's for you to better to hear me. And today we're going to discuss the processing of this real-time data. So in processing of real-time data, there are two main stages or two main approaches types. So first one is coding. So how to encode temporal data for it to be less to consume the disk space, for example. And so in coding, there are two types: it's lossy and lossless. So lossy, for example, is the autoencoder approach, and it wasn't mentioned in this article. I don't know why, because it is from 2013, and I think it should be there, but it wasn't. And so it's the lossless methods, is the Markov models like context tree Wayne method. So we won't discuss these methods, and the whole idea of this presentation is to give just an overview. So when I started to read all these articles about context-free weighing and other algorithms, I realized that they're too big. They're about 30 pages each, and so they're too complex to understand in just 1 week. So today it will be just an overview. And so the next type is sketching. Sketching, as it's called in this article, it's a tool for summarizing temporal data. So it's some kind of representation of this data. So it also has some types. So it's native format, like we can show data with sliding window, for example, just some piece of data, real-time data. And also it's some sampling time series. And also sketching can be in a derived format. So derived format is some applied function to this real-time data, like random projection, histograms, average count, and so on. And of course, it's a combination of above types. So for sketching, for example, there is a work of Garohalakis and Rastolgin. It's presented in the article Querying and Mining Data Streams. So the basic idea here is that we don't work with the real-time data as a whole. We work with its representation. This, yes, representation. So some kind of subsample this data, take this data as a representative subset of real-time data, and then we apply some methods. So for example, the as you can see on the slide, to count an average. So for example, we have a statement: select some aggregate from D is this, where D is odd. So we, if we want to take some average, we take this subsample of our data and count some average, and then we get some representation. So we got 6, but in real it was 7. So in this case, we don't give strict guarantees that we'll get the right result. We just give them some probabilistic guarantees, so that our answer won't be with 90% probability. It won't exceed one interval. So for example, plus minus 1 or something like that. And it's a very big article, so there's not only average, so they also touch a lot of aggregator function, and also they touch a lot of techniques like histograms and how to build histograms basing on this subsampling method. And I think if you're interested in how to do this and how to apply it to real-time, to your real-time system, for example, you should take a look at this article. Um, um, the next problem that we might face in processing data is that most of the algorithms, they impose linear or some linear memory assumptions, but having this assumption, we cannot really reflect the changes in distribution of our data. So for example, when we get some data stream and it has some distribution that we know after a year or two, it may change. So, and we should somehow reflect this situation. And in the work of Sabianchi and Lugosi, that's called On Prediction of Individual Sequences, they proposed an approach of mixed online and batch learning by FTRL algorithms. So FTRL algorithms, it's follow the regularized leader algorithm. So its basic idea is that predictor is based upon some experts. Experts are some functions that can suggest the further action or maybe not action, maybe the prediction. And in each round of learning a new expert or prediction, a new expert is chosen to that shows the best results upon previous predictions. So it is also quite a big article and quite complex to understand. I just found some good video how to show how follow the leader algorithm works. I hope it will work. Or not. We should wait for a while. Or I will reload the computer. Okay, so it will not start. Maybe we should go to YouTube. Ah, that was a bad idea. Okay, we'll go further. So no video for today. So another problem that we might face that our input rates, they exceed the computer capabilities, well, for offline learning and prediction algorithms. So in this case, we should, like in the example of these aggregator functions, we should approximate our representation, and that's called data stream approach. The last mentioned in this article works was about Stanford Data Stream Management System. So it's based upon this data stream approach. And there's a book of how to work with these data streams by Muthukurishan in 2005. Yes, so but there is still a major challenge of efficient statistical inference for general models. So we have same problems here, like changes of distribution and so on, that we should face and how to work with it. So if, for example, you see that your computing capabilities are not offline learning and yes, and prediction algorithms, they exceed your computing capabilities. So you may want to see this Stanford Data Stream Management Systems and maybe, for example, read that book. So yes, again, some lags. We should wait for a while again.
Hang out.
I think we should wait. No, it's okay. Nothing bad. What? No. Yeah, this one. What? This one? It can be closed?
Yeah, it can be.
No?
Yes. Yes.
Okay, I'll close it. Are we sure?
Yes.
Yes. So computers cannot even cope with Microsoft PowerPoint. I'm not talking about real-time data processing. Okay. Uh, okay. So that was about processing, but still we should understand that imposing real-time algorithms, we should be ready to some hardware and system changes, and we should somehow cope with high demands and on hardware and system infrastructure. So there's a problem and there's no general solution to it. So there's like a solution of Google, it's Google file system that I'm not really familiar with what it is, but I think it's some kind of presentation of how to work with this, how to build systems that are highly loaded. So we of course should have tens of data acquisition machines to funnel the data in thousands of processors to using very fast interconnects. And of course, it's this building these systems demands having qualified engineers on such projects to not only to provide a way how we process it, but provide an appropriate hardware for this and system demands. And surely these systems are difficult to replicate because of a lot of data and a lot of data flows and data changes, and it's expensive to maintain. And as I said, it requires a good complement of reliability engineers. So also there might be some errors in the system or in data that can break integrity of data and may lead to burst of errors. So we are talking about real-time data, and if we calculate, for example, some sliding parameter that depends on previous observations, an error in one observation will lead to errors in the future. So that's a problem, and there is a book and solution. So it's a theory of error connection for communication over channels prone to burst errors, and it's McCulley in 1990. He published this book. So this theory, you can read about this theory and how to cope with these situations and how to provide data integrity even if some hardware fails and so on. So what else should I say? Yeah, so there, and of course there is no general solution on the current day. So like there is no framework that you can apply on your servers and it will work and it will guarantee that your data will be consistent. Nevertheless, your hardware breaks and fails. Your HDD, for example, or SSD fails. So there's no general solution. They are confined only to proprietary systems like in, for example, this Google file storage and so on. So that's also a challenge. So that's it for this first chapter from my side. Here are some references that you may find useful if you face some real-time systems, building real-time systems. And so that was some slide. That was a glance on those algorithms of processing data. So again, I just didn't manage to dive into this deeper into this field and into this algorithms because they're quite complicated to understand for 1 week. So any questions?
It's quite complicated to understand that in half an hour.
Yes. I really tried to read those articles, but I've spent 2 days to understand this. I forgot. Yeah, this context tree weighing method, and I didn't understand it, so I decided just to give some overview of those algorithms. On this presentation, I think you'll have.
Maybe you may show the video.
On YouTube. Just press it. Ah. No, it doesn't work.
Yeah.
Maybe we should have tried this at Chrome, yes.
Unavailable in Russia.
Yes. No, no. For some reason it doesn't work. Ah, yeah. Great. I don't know why. So here we see that there was a leader, this one, and then a robot moved to this leader, and the leaders were reassigned. So a new leader was chosen, and now a new leader, and so they like consequently choose a leader for a certain bot, and they behave like him. So for now, they are just in a process of assigning this leaders, and then they will go together. So like this. And so each of the robots is following its leader. So that's the basic idea of this.
Like a snake.
Yeah. So yeah, that's it. I think I should copy this presentation on the desktop, yes? Okay.
It's a test manager also. Because it also uses some resources.
What do you think? Closing this explicit?
Yeah, close this split and close test manager.
Oh yeah. So here's my presentation here. Okay. So that's it.
I have a question,
Mm-hmm.
but it's like point of my interest. I couldn't really understand what you said, like not everything, but I could catch some ideas. But I have a question. Do you think you're gonna use these algorithms in real life, and do you think it's going to help you somehow? Using an application of this theory in real life?
Sure. Like for example, well, as an example, like that was on the previous seminar. So if we are considering an issue of predicting, for example, some stock market prices of some options or something else. So this issue is quite complicated because a lot of things they affect this parameter, and we should consider a lot of real-time data from different sources with different time lags, with different representation, and they which may also fail. So to provide some prediction, for example, for our strategy for us to have some money. So in this case, it's absolutely applicable, and all of the system and all of these algorithms can be applied to this. In some maybe other closer to our ordinary life. I cannot really imagine this such situation where it may help. Yes, but for now I'm working on a project of recognizing, transcripting text from the audio stream, and so we may consider this audio stream as a real-time data. And so, based on this data, we should calculate a lot of parameters like text, like the mood of the speaker, like the speaker, divide the speakers, and so on. So in this case, we have a lot of tasks that are performed upon one data stream, and this task also should be somehow scheduled. This task also should be, if, for example, one of these submodules fails, so we should somehow provide a meaningful response with some available data, maybe somehow guess what value our failed submodule would have produced, and so on, based on other parameters, for example, characteristics of our data. So in this case, some of these algorithms, I mean, not all, I think, but some of them may be applicable. So yes, there are applications.
Thank you.
Thank you. I like this picture.
Я на флешку что-то не скинул.
Slides.
Ah. Okay, hello everyone. Today we're gonna talk about frontiers and massive data analysis. This is the 6th chapter. Today we're gonna talk about resource, trade-off, and limitations. This is the 6th chapter from Frontiers in Massive Data Analysis book. And today I present something about current state of the art and the gaps in fundamental understanding of computation over massive data sets. The committee focuses on general principles and guidelines regarding which problems can or cannot be solved using given resources. So massive data computations uses many types of resources, and at high level splitting it at high level they can be split on 3 main categories. The first one computational resources such as space, time, and number of processing units, and the amount of communication between them. The second one is statistical or information theoretic resources. It contains some resources such as the number of data samples and and their types. For example, where the sample is random or carefully selected by the algorithms, whether the data are labeled or unlabeled, and so on. And the third one is physical resources. It's amount of energy used during the computation. So the use of these resources has been studied in several fields. Reviewing the state of the art in those areas, even only in the context of massive data processing, is a task beyond the scope of this report. You can find this scope in another chapters of book, and if you're interested in it, just read in the special articles and so on. Okay, the first chapter of my presentation is relevant aspects of the theoretical computer science. There are 6 general categories, and we will talk about each of them a little bit. The first one is tractability and intractability. What is that, and what does it mean? In introduction, I want to say that theoretical computer science studies the strengths and limitations of computational models and process, and there are 2 main connected goals. The first one is to discover and analyze algorithms for key computational problems that are efficient in terms of resources. And the second one is how to understand the inherent limitations of computation with bounded resources. Yes, as I say, these 2 goals are naturally interviewed. In particular, understanding the limitations often suggests approaches for sidestepping them. Okay. Yes. Also, in this section, the committee surveys and something like illustrative list of concepts and notions developed in theoretical computer science. Okay, let's talk about tractability and intractability. As you can see, most of the natural problems are known to fall into one of these 2 categories. So specify, we have to start from P and NP problems, and I think that everyone have some meaning about what is that, but I just talk a little bit to remember you. So one of the central notions, not totally in massive data, just in information technologies or in mathematics, is in understanding computations is that of polynomial time. Polynomial time algorithms have the following attractive property: doubling the input size results in running time that is only a fixed factor larger. This should be contrasted with algorithms with exponential time. Here, doubling the input size can increase the running time in a much more dramatic fashion. As such, problems that have polynomial time algorithms are often referred to as trackable, and another task called intrackable. Yes, the main problem we have that in P complete problem. That such problem said to run in non-deterministic polynomial time. It's called in P, and though this okay, just let's remember an example of in P complete problem. For example, it is a traveling salesman problem when you have a set of cities and distance between them, and you want to have a tour over a given length and visit all the cities. And then another example is it's enough, I think. We all studied this salesman problem, and the difficulty of such problems comes from number of possible solutions in order to find the good one. Also, it is known whether an NP-complete problem can be solved in polynomial time. This question is called P versus NP. It is one of the central open problems in computer science, and as I say, in mathematics and all scope of information technology. And it is widely such okay. Let's move on and look through sublinear sketching and streaming algorithms. In the search for efficient for good algorithms for large-scale problems, researchers formulate more strange models of computation. One of these notions is particularly relevant to massive data is that of sublinear algorithms. They are characterized as using an amount of resources much smaller than the input size, and often exponentially exponent I don't know how to okay, just much smaller than the input size. Yes. This in particular means that the algorithm cannot read or store the whole input, and instead it must extrapolate the answer from the small amount of information read or stored. One of the popular computational models of this type is data stream computing. In the data stream model, the data need to be processed on the fly. It means that the algorithm can make only a single pass over the data, and the storage used by the algorithm can be much smaller than the whole input size of all data. Specify streaming algorithms processed by computing and summary of scratch of the input, which is much shorter, but nevertheless it can not satisfy us, and we have to approximate the desired quantity. Perhaps for many problems of counting the number of distinct elements in a stream, it is an example of problem of streaming. So how can we count how how can we count distinct elements in a stream if we don't have all the data? So of course we can make something like a copy of them and then count, but we the main idea of streaming do not store all the data. So this task is known to require space that is at least as large as the actual number of distinct items. However, it is possible to approximate the quantity using only a logarithmic amount of space, and this problem known and solved by this way, and you can read about this by reference from this book, from this chapter. So other models of sublinear computations includes sublinear time computation, where the algorithm is restricted to using an amount of time that scales sublinearly with the input size, and approximate property testing, where one tests whether the input satisfies a certain property using few data samples. Okay, the next category is communication complexity. The field of this category studies the amount of information that we need to be extracted from the input or communicated between two or more sharing parts of the input to accomplish a given task. Yeah, this field connected with NP completeness problem and communication complexity techniques make it possible to prove that some tasks cannot be accomplished using limited communication. So, as example, consider the following set disjoint the problem where two parts want to determine whether two data sets of equal size, each held locally by one of the parties, contained any common items. It also has been shown in order to accomplish this task, the parties must exchange a number of bits that is linear in the size of dataset. Okay, the next category is the parallel algorithms. I think everybody knows what is that, and as a general, in general, these algorithms studied questions is to understand for which problem one can obtain a speed up using parallelism. Many models of parallel computation have been studied, and perhaps the one of that has attracted the greatest amount of attention is a class of problems having polynomial sequential algorithms for which one can obtain exponential speedups by using parallelism. Such speedups are known to be possible for many problems, such as finding a perfect matching in a graph. That problem calls for finding a subset of edges in a graph that contains exactly one edge incident to any vertex, given a set of nodes and edges between them. There are also problems that are there are also known problems which cannot be solved by using parallel algorithms. Computational learning theory. Yes, this field studies the computational aspects of extracting knowledge from data. Specify it addresses the following question: how much data and computational resources are needed in order to learn and concept of interest with a given accuracy and confidence? For example, a well-studied task is to infer a linear classifier that can be separate data into positive and negative classes, given a sequence of labeled examples and using a bounded amount of computational resources. computational learning theory has natural connections to statistics, and it includes known and studies algorithms by all of us, like naive Bayes and other statistical classifiers, and so on. Okay. Also, I have a third part of my presentations, gaps and opportunities, but I think we can talk about this part on next class. And so that's it for today. Thank you for your attention, and if you have any questions, go on. Okay, in summarize, we reviewed some aspects of the theoretical computer science, and I talked about all of these category, and if you have some specified question, I can try to answer for it.
Yeah, I have one. I didn't get what ideas are proposed for these theoretical aspects. Uh, what we need to do? We need to develop parallel algorithms. Yeah, it's an obvious thing. We need to learn computational learning theory.
Yes, I I understand your question, and the answer is that we have to to use these aspects not like one by one. We have to understand the task we want to solve, the problem we're gonna solve, and as an example, I talk about known problems which we cannot to solve with such of these algorithms, and you have to understand that we don't need to use all of these techniques like a blind, like we, don't know, like like blind engineer. I don't know. It we have to read some known and overviewed problem about these techniques and understand that from time to time we don't need to use, for example, parallel algorithms or computational learning theory that doesn't applied to us. So this is the main purpose of my chapter, just to introduce you of known aspects, and of course on the next class we will talk about gaps and opportunities. And did I answer for your question?
I think that's the main message from your report is we need to develop all these aspects: communication, complexity, computational learning, parallel algorithms, and all these aspects are relevant to the lack of computational resources. In case of massive data, we need more and more computational resources, but sometimes in case of NP problem, we can't cope with massiveness.
Yes, we have to.
Can't plus one server and just one, or in doubling your string. When your string doubles, you need to add some exponential
Yes.
of resources, and it is inevitable.
Yes, of course, we have to think about all of these aspects, but particularly sometimes it cannot be completable with to our given task. And for example, if we have NP problem, we have to try to ask another question, which can be solved by exponential time.
Okay. Other questions? Okay. Thank you again. I'll see you next time. Next time also we'll listen to the 7th chapter. Okay. Thank you.
Thank you too.
Mm-hmm.